Very good. So our speaker today is Yang Liu from Sisa, Italy. His title, as you can see, Hypergeometric Functions and Heat Coefficients for Non-Commutative Tori. Yang? Yep.
So thanks for the introduction, and thanks for the organizers for the invitation. It's my great honor to give a talk in this global non-commutative geometry seminar. So my topic today, actually I think there already were like several talks along this seminar that's related to this topic. I think the very first is the Raphael Ponch's talk. It's about the differential geometries like a pseudo-differential calculus on non-commutative tori. And then I think Masu gave a talk about this Newton divided difference, right, in this modular geometry business. And a few weeks ago, Oscar gives a talk. It's somehow closely related to what I'm going to talk about today. So yes, today I'd like to report some really technical results. So probably at the end, the notation will be very, very heavy. So I will start with some motivations, like to warm up. So I think the big program, the question here is somehow to do like move part of a central definitions in Riemannian geometry, namely the notion of curvature and the matrix, right, to non-commutative manifolds. So the model here is the usual the spectral geometry. So how to detect local invariance, right? So from a purely spectral fashion. So one can, so let's start with a nice manifold. Mg is a closed Riemannian manifold, and basically, so one should think of replace the role of this metric tensor by a geometric operator. You can use, for example, like for the Laplacian operator or a square Dirac operator, plays the role of metric, and then to get a local invariance, so we can look at the small time asymptotic expansions from this heat trace here. Oops, sorry. Here, so we can view this as a functional in F. So in differential geometry, probably the formula is written in terms of the Schwarz kernel. But in order to move the notations directly to the non-commutative case, I use this trace. So each coefficient viewed as a functional can be shown that it is continuous, absolutely continuous with respect to phi0. Phi0 here is the volume functional, and then there is a smooth, rather Nikodym derivative. So in here it's just each coefficient. The density here is a function, smooth function on a manifold. So basically, so they are the derivatives of the symbol of P. So for example, if we look at the Laplacian, so the first term, the V0 term, is you get a volume, and the functional density is the constant function 1. And here we are mainly focused on the second term, so which is up to a constant. Then you get the scalar curvature. So that will be our model of a scalar curvature. So to non-commutative torus, and then to probably more examples, for example, like a theta deformations. So I have some noise in the background. Can everyone hear me clearly? So I hope my connection will still stable, right?
Yes, we can hear you very well, despite noise.
Okay.
Yeah.
Okay, good. So from this heat trace asymptotic and equivalent way, I mean, is to look at the spectral zeta function. So, and for instance, the existence of the heat trace asymptotic can imply the meromorphic continuation of the zeta function. So, and then each heat coefficients will correspond to a special value of the zeta function. For example, like later probably we'll need in dimension 2, this zeta function at 0 is basically the second heat coefficient so of P. So for example, if you take F to be the constant function 1, and then this is the trace of the projection to the kernel is the dimension of the kernel of PG. So namely, this is the zeta function and the second heat coefficient, they are different by a constant. So okay, so let me briefly review the stories of this modular or conformal geometry. So on non-commutative tutors. So it is, so the project sort of, it started with Kontrakov's paper about this Gauss-Bonnet theorem. So the setting is the following. So the way, so on non-commutative, the classical differential geometry, like partial derivatives, you can have say a flat Laplacian, which represent a flat background metric. So to introduce a curved geometry, so for example, to mimic such a conformal change of metric, so we are looking at such a perturbation on Laplacians. So this is a change from a flat Laplacian to a curved Laplacian. So by putting these vowel factors on the two sides of the flat Laplacian. So this well, this process, I think it's not quite, it's a little bit tricky. So I will not dig into the details. So, but if you read Alan and Henry's paper carefully, I think there's some tricky stuff. But let's just take this perturbation as a result. So, and then by direct analogy of the result of manifold just mentioned before, so you can take somehow the functional density of the second heat coefficients as a notion of the corresponding scalar curvature for such metric G prime. So, and moreover, right? So basically the second coefficient, so is the sort of the analog of integration of the scalar curvature, right? So now the Gauss-Bonnet theorems in this setting is basically saying that so phi zero is the canonical trace of non-commutative. So at the very beginning, so what Kohn and Trekov shows that they can compute the integration of this scalar curvature. So, and then they can show that the result is zero. So that's the sort of the first version. So of the Gauss-Bonnet theorem. So oops, I should go. And then later, I mean, so after Alan becomes a master of Mathematica, I think he can compute this full scalar curvature. Like so at the beginning, I think he somehow computed the integration, and then in the middle he had the full information of this this scalar curvature. So and then he and Henry like started to think about, okay, so can we do more, right? So since we have the more information, so what can we do for this once we have this full information of the modular scalar curvature? So in here, so on the other hand, I think this the Masu and Fassad, so they did like the independent computation. I think they even use different computer software to compute this modular curvature, and then the result, of course, agrees. So that's sort of the first validation for the full formula of this modular scalar curvature. So, and then in the next step is so once you have this full scalar curvature, so in the Kolmogorov paper, so they propose you can move some variational problems so into this onto this non-commutative manifold. So basically, let's consider this this conformal class of metric, right? It is parameterized by this log vowel factor. So e to the h is the conformal factor. So then this h sort of is a coordinate at the tangent space of the conformal class of metrics. Suppose you can find some functions on h. So this is a function on, say, abstractly speaking, is a function on self-adjoint elements, like on non-commutatori. So it is geometrically speaking, it's a function on the conformal class of the metric. So you can consider the following variational problem. So you want to consider the variation. So the function of gradient is defined in the following way. So you can consider a sort of a directional derivative along this this self-adjoint element along such a direction A. So and then the left-hand side will be a linear functional, right? So in A. So and then it can, if this linear functional is if we can show this linear functional is absolutely continuous with respect to, say, this volume, this canonical trace, this volume functional, and the density, the Radon-Nikodym derivative will, so we will call this the gradient, right? So okay, so then the first function we can choose, we can think about is indeed the Einstein-Hilbert action. So in terms of the zeta function, as I mentioned, that the zeta function at 0 and the second heated coefficients, they differ by by a constant. So let's consider this functional, right? So for each h, so in here this operator depends on h, right? So and then you take the zeta function evaluated at 0, then you get a number. So you get a function. So this resembles the integration of the scalar curvature. So and then one can indeed show that. So for example, we want to show this is a constant function, right? Then so we want to show this is, so then we just compute the derivative. If we can show the derivative is 0, and then it's a constant function. So in Kolmogorov, so they gave a sort of a variational proof, right, to show this gradient is 0. It's 0 because of this coefficient is 2 minus 2, right? The dimension of the non-commutator is 2. Namely that you don't even need this information, right? So then you can prove the Gauss-Bonnet theorem. So that's the first. So in a way that so then then it's like a, so we have not yet used any information here for this one, right? So when you consider the variation of zeta function at 0, and then we can go deeper. So to find another functional which is more interesting in terms of the variation. So the model they took is the model of this Ray-Singer determinant. So the result is recorded in this I think it's a famous paper by Osgood, Phillips, and Sarnak. So in which they study the variation of the Ray-Singer determinants, and then as an application they prove the uniformization theorem on Riemann surface. So and Alan and Henry took this as a model, and then move this functional so onto non-commutative Tori. So here this functional is a normalized version of this determinant, because look here you have a log, right? This is, so it's like, because this is a log determinant. So after ignoring the log, it should be division, right? It's divided by volume. So that's why I just called it, this is a normalized Ray-Singer determinant. So you adding this term, then you can, this functional has a minimum and a maximum, I think so. So and then you can so by this analogy with the classical result on Riemann surface, so and Kohn and Moscovici so took this the gradient of this functional as a definition of curve. So in a way, so for example, if you view the previous version, the second unit coefficient, as a analog of scalar curvature, probably let's call this version, this from variation, like a modulo, the analog of Gaussian curvature. So very similar to the commutative case. So in the commutative case, we know that the Gaussian curvature and the scalar curvature probably differ by a constant of 2. So in this case, it's a little bit tricky here. So that's the exact relations between this scalar curvature and the Gaussian curvature. So the reason here is that abstractly, you can think of these elements as a sort of a second derivative of your metric coordinate h, right? So metric is the scalar curvature, it's a sort of a combination of second derivatives of the components of the metric tensor. So here, so we're fighting with the non-commutativity between this h and all its derivatives. So that's the essential difficulties we're fighting with. So that's why you have this conjugation here. So you cannot freely move this h in front. So it leads to the idea that we are doing some rearrangement. So this idea, I think, is first used in a Contreras paper. So here, you have a sort of a conjugation operator acting on this element, right? So the conjugation operator is the exponential of this commutator derivation. So now you view this as an operator acting on these elements, and then you integrate. So I will call this a sort of a rearrangement operator. I think the whole talks about, so I will report some sort of interesting features we're seeing in this rearrangement operator. So now if you view x as a purely variable, right? So you compute this integral, then you see this this operator can be written in terms of sort of a functional calculus, and the underlying function is such a sinh function. It's a quite interesting function. For example, it's the same function used to produce this a roof class, right? So in the for example, in the index theorem, RTL single index theorem. So basically, so the idea is that we can sort of grab the information of this rearrangement operator by this underlying spectral function. It's like so we will grab the information of a characteristic class by the underlying genus, right? So here are more interesting features about this modular scalar curvature. So here is the full formula for the modular scalar or modular Gaussian curvature. So yes, as I just mentioned, it is a second derivative of the metric, right? So in the commutative case, this will be a number, just a differential operator. Well, so because of this, the facts that the h and the delta of h, the derivatives, they do not commute. So this phenomenon we're dealing with. So therefore, you have this coefficient, this rearrangement, new coefficient, rearrangement operators in front. So it is somehow, yes. So that's somehow this is called the modular part of this curvature. So it is you can think of this as because this commutator, so generated by h, is the infinitesimal action of the modular operator associated to the, here I should say, here phi is the rescale of the volume, the new volume. So we have phi 0. Oops, sorry. So we have the phi 0. This is the volume form for the flat metric. So now, so by this just this rescaling, so this phi is the volume form for the curved metric. But due to the non-commutativity, this phi is no longer a trace. It's only a state, and then a weight. Probably not. It's not normalized. And then it has a modular operator. So it has a one parameter group of these modular automorphisms. So and then this conjugation by h is the, oops, sorry, is the generator. So sort of so the appearance of this rearrangement operator reflects the sort of these interactions between this modular automorphism and this underlying smooth structure represented by this classical derivatives, right? These are the basic derivatives on non-commutative. So it is the interaction between this sort of a non-commutative derivation and the classical like smooth structure. So again, the interesting feature is about the underlying spectral functions about this rearrangement operator. So for example, for the one variable function, so it's you can see the generating function of Bernoulli numbers in this. And on the other hand, since this Gaussian modular Gaussian curvature is sort of a variation, right? So the right hand side sort of is the Euler Lagrange equation of some variation. Therefore, one expects that these two coefficients of this Euler Lagrange equation has some relations, and then yes, and so indeed there is a quite so compact relations between between these two, like K and H. So this so through this variation, and since one can compute K and H explicitly, and then by verifying this, they indeed fulfill this these simple relations. Now, so we have it achieves a really like sort of a conceptual validation, right? So for the computation. So it's I think so. This is there are some difficult computations behind. So okay, so here's some result about this. So this is some invariance property of this modular Gaussian curvature on the Morita equivalence. Probably I will skip this. So if anyone interested in this, we can discuss this in a question section. So to end this the motivation part. So after that, there are many papers. So many similar computations has been carried out on non-commutative 2 torus or non-commutative 3 torus. So for example, like I just mentioned a few more names. So I apologize. I like others like so I have not yet mentioned here. So and then there are 2 surveys by the first survey is written by Moskowitz and Lash, and the other surveys is written by Fazad and Masoud. So therefore, there you can find a more complete references on this project. So here, so I will. So my result here is intended to deal with to develop some technical tools to go beyond conformal geometry. So in here, right? So in here, so you do conformal change of metric. You bring in only one coordinates, and then we are fighting with this the difficulty that the H and all the deltas of H, they do not commute. So what about we bring in like a more coordinates, like beyond conformal? What happens? So basically the essential question, right? So it's from the discussion. So the technical part is we have to compute these heat coefficients. So for more general second order differential operators. So okay, so to continue, let me, so since we're just going to talk about just some more technical questions, I can work with not only non-commutative 2 torus, I can work with say non-commutative M tori. So here are the basic notations. So this algebra of non-commutative tori is generated by unitary elements. So you can think of this uj, you can think of as functions e to the I xj. So xj will be the coordinates of the x1, xm will be the coordinates of M torus. So then you have these basic derivations. So sometimes I use this. So the classical notations we use delta, right? So if here I use I use this nabla, like this nabla j will be the sort of the partial derivatives, like partial ln xj, like compared to the classical notation. And this phi zero is the sort of canonical trace. We are taking the constant term in the Fourier expansion. This corresponds to the Lebesgue measure on non-commutative on the usual M torus. So with this volume, so phi zero, you can define this inner product like following this GNS representation construction. So and then we have a Hilbert space. So and for example, here is the analog of the flat Laplacians on torus. So here, here I would like to compute this heat kernel asymptotic for a more general class of differential operators, more precisely a Laplacian type operator. So let's consider a general second order differential operator using this partial derivatives. So we can, any second order differential operator will be of this form. So here is a KSL, they are the coefficients for the leading term, and these are the coefficients for the first order term, and P0 is the constant term. So the coefficients, they are elements in the smooth non-commutative tori. So to state my main results, probably I will need the notion of about symbol of differential operators, or more generally pseudo-differential operators. So all the symbols, they are contained in functions. So with value in the algebra of smooth non-commutative tori. So in particular, like what happens in the commutative case, if we are dealing with polynomial symbols, and then if we are dealing with differential operators, their symbols, they are polynomials in Kasai. Kasai is so you can think, so this algebra is you can think of this as the function on the cotangent bundle of non-commutative M tori. So that's the analogy here. So to get symbols for differential operators, it is quite easy. So you can just simply replace each basic derivation delta j by psi j. So that's the symbol. So basically, so you can think of this heat kernel asymptotic as a black box. You are throwing your inputs, they are the symbols of your differential operator. So the outputs will be certain complicated combinations of the derivatives on the symbols. So that's sort of a black box, usually very difficult to compute. So okay, so now I will add more assumptions to make sense of this to make sense first, so we can to make sense that first step to the heat operator, right? So I will assume P is a essential self-adjoint, means that these eigenvalues will be real on the real line. So as in the here I will assume this coefficients of the leading symbol Kij, that they mutually commute, and I want this matrix to be symmetric. Kij is equal to Kji, because look at here. So it's a polynomial, right? So we are expecting that the coefficient between psi I, psi j, and the psi j, psi I, they are the same. So that's why this matrix is symmetric. And I also want this Kij to be to be self-adjoint, like a real value functions. So, and then so the usual condition, right, to get this heat asymptotic is, so we want this symbol to be positive. So in this functional analytic setting, so this for fixed psi, so we get an element in this pre-C star algebra. So we want this element to be positive for non-zero psi as the usual case, and then we can run the standard arguments in the elliptic operator theory. So here we have a Kahn's pseudo-differential calculus. We can, so for example, then we can say we have this P has compact resolvents, right? So then you have these eigenvalues on the real line, and then because of this positivity on the leading symbol, this so all these eigenvalues has a lower bound. So then we can write the heat operator as a holomorphic, in terms of a holomorphic functional calculus. So, and then to study the trace of this operator, so we are looking at it sort of a approximation on symbols on the resolvent part. So here, so the reason is that so if we suppose we can compute the second coefficients, right, and then we can get in this case the second heat coefficient is proportional to the Einstein-Hilbert action, right? So if we consider similar variational problems of the like what we just mentioned for the modular Gaussian curvature, right, and then we will get the analog of Ricci curvature, right? So that's by comparison with the classical result. So the classical result says that if you only do variation inside a conformal class of metric, then the derivative will be the scalar curvature. But here, so since we are allowing like general Kij, if we can do variation like for general, like for general metric, so I mean this Euler Lagrange equation will contains the Ricci curvature, in which we can find the corresponding part for the Ricci curvature. So that's sort of a long-term plan that sort of one of the motivations that why I want to compute this second heat coefficient. Okay, so let's in order to state my main results, so let me review this algorithm to compute heat coefficients following pseudo-differential calculus. So before doing that, I just mentioned two other references, like so there contains there are other approaches to compute these heat coefficients, but here we will mainly follow this pseudo-differential approach. Well, just according to my knowledge, I think all these approaches basically we are facing the same obstruction. So sort of they are parallels. They're like so none of them have shown like a striking advantage to the other. So okay. So to get to the heat coefficients, so we start with the symbol of our second order differential operators. So here is the leading term, here is the degree 2 term in psi, here is the degree 1 term, and here is the degree 0 term. So here lambda,
so it's the resolvent operator. So it is sort of a symbol of degree 2. That's why I matched it with the leading term here. So and then so this inverse, the existence of the inverse is guaranteed by the ellipticity. Like I assume this P2 is actually is a positive element for non-zero psi. Therefore, the inverse makes sense. So then this inverse will be the first approximation to the symbol of the resolvent. So and then using this the symbol calculus in the pseudo-differential operator, you can continue to construct like B1, B2, B3. So and then the upshot is the following. So this Bj will lead to the heat coefficient Vj. So the heat coefficient Vj is given by following this integration. So on this Bj. So here, the first, this part is the contour integral. So from the contour integral where we define heat coefficients and integrate. So integrate against this psi variable is coming from you are taking trace, right? So you are taking trace from there is one of the components of this symbol calculus is that somehow you can compute the trace of a pseudo-differential operator by integrating its symbols along this psi. So this integration in psi, you get a trace. So here what are the B2 terms that we are interested in? So here I'm showing you. So here I have no intention to to bother you to look at this long formula. So here the pattern that I would like to point it out is that all this B2 or even Bj term will be a sort of a many numbers of terms, but a finite sum of the following form. So you have some powers of this B0, like and in between you are inserting the derivatives of the symbol. So that's a general pattern in here. So I mean, even in the B4 term, if you look at the paper of Kohn and Farzad, so there are like many terms like so we have to collect and then analyze and analysis. So here, okay, so the first general feature is that in each Bj it's many terms, but still a finite sum of terms looks like that, some powers of B0. So and with some rows in between, where these rows, they are derivatives of the symbol of P. In particular, they are polynomial in psi. So sort of the easy part. So the hard and versus easy is in the sense that the B0 has inverse, right? So while this row has no inverse, they are polynomials in psi. So then the next step is so we first do this rearrangement. How do we sort of factor out these B0 zeros? So we introduce here basically is just a definition. So we introduce for any elements. So we introduce a super subgroup, say J. It means that this AJ. So when acting on this a tensor like row 1 tensor row n, so it's just multiplication at J slots. Here is the 0 slots from the left, like the n slot on the right. So there are many other slots in between, so indicated by this index J. So and then that's the first step. We can, by using this these notations, we can basically factor out all these B zeros. So then the good thing is that the B zeros contains all the lambdas and the inverse. So that's the hard part. So in terms of figuring out what is this integration. So this process. So now we're taking this integration into account, right? And then by the formula I just shown you before, so the heat coefficient will be the sum of terms like that. So this process from row 1 to row n to this integration, basically, so we have a linear operator acting on this row. So this integration, so abstractly, so we have a linear operator. So I will give a name f of sub alpha a. Alpha so comes from the powers of b0. So this index alpha, and then so this a is the coefficient matrix of the leading symbol of our underlying geometric Laplacian type operator. So here is so if we accept that we have this abstract operator, right? So through this algorithm, right? So basically, we can by apply this sort of a rearrangement operator f alpha onto all these terms, a bunch of lengthy terms here. So then we get a general formula of the second heat coefficient. So here is a bunch of terms. So here is the full formula for the second heat coefficients. So for this general operator P. So probably I'm moving too fast. So, but yes, but so the pattern here is that you have the derivative of symbols in here. Then you have these rearrangement operators in here. So then the next part is that I have to tell you the more interesting features about this rearrangement operator. So that's the so that's where the notation is getting quite heavy. So in the literature, so I think so. For example, what Alan did is that so at this stage, I think Alan is trying to do this integration on psi first. So and then you're doing this rearrangement. So here's some small progress. So I stressed here. So probably we can do this together. So sort of combine this together to make the computation. So sort of to get some simplifications in the computation. So oops. So okay. So so there is a technical result called a rearrangement lemma. So roughly speaking, the rearrangement lemma is basically the way how to compute integrations like this, how to compute the integral like this. So basically everyone has its own way to compute the integral. So then we get so this rearrangement lemma start with this Kontrakos paper, and there are different variations depends on on preferences to compute the integration. So and then Matthias Lasch will give a more systematic treatments to deal with those integrals, so which has a huge influence on my own way to compute these integrals. So okay, so the interesting feature here is that this rearrangement operator consists of two parts. The first part is a formal is this exponential part. So this exponential part takes care of this integration in psi. So this comes from the Gaussian integral, which I will explain in a minute. Basically, it's like the result is that integration in psi can be computed by taking derivatives. So, and the other interesting part is that there is a hypergeometric integral part in looking at here. So I will explain these notations in two parts. So here this matrix here is a sort of a linear combination. So U is a point on the standard n simplex. U is a linear combination in the following way. So I would first of all I will point it out that these coefficients they are the boundary equations of the standard n simplex. So that's the first interesting part. So basically you take the boundary equations of this n simplex, and then you match it with this A, the 0, 1. So this superscript represent that this multiplication at a J slots, right? Different type of multiplications, because we are acting on tensors like that, row tensors like that. So we have different way of doing multiplication. So here the coefficients, they are the boundary equations of this the standard in simplex. So I think the notation will become much more clear. So if I briefly outlined how to compute this integral. So this here is the definition of this rearrangement operator, right? F sub alpha. So I want to compute this integral. So basically there are two steps. This contour integral and integration on integration in a psi variable. So first of all, let's say we have a lemma which takes care of this contour integral, which leads to this hypergeometric part. So now and then, because this row 1 there are polynomials in psi, then sort of I can factor out all this psi, right? So into this integral. So basically we are looking at the integral of this type. So where f psi is a polynomial. So if we have a lemma to deal with this contour integral like this, and then integration in psi is simply a Gaussian integral, right? So this is because B is a quadratic form in psi. like this is a sort of a second order homogeneous polynomial quadratic form in psi, and then you have exponential, you have a polynomial. So this result is known. So this integration is known as a Wick's theorem. So you have this Gaussian integral. So for example, if we look at such type of integration, so on monomials, so you get really lengthy formula, but it's a sort of a much more beautiful way to write this is to look at the sort of a generating function. You can view this so if you know how to integrate, so if you know the value for monomials, right? So and then you know the how to integrate in general any polynomials. You are sort of taking the generating function. You can see that this is indeed the exponential function. So here is a more of a fancy way to write such an integration. You can sort of turn this integration as a sort of a by differentiation. So which somehow explains this part, this exponential part in the theorem. So and then yes, so then the next step is how to deal with this contour integral. So in the commutative case, you only have one term. So then which is simply there's an exponential. Sorry. So there is an exponential here. So there is a e to the minus lambda here. So then here I have an exponential. So if we have only one term, it's simply a exponential. So if we have a so the so in general, since this non-commutativity, so we have the sort of a different possible way, right? So doing this multiplication from the left, right, from the middle. So we have from 0 to n. So from 0 to n. So let's view this as some just a formal variables, right? So we consider integrals like this. And then there is a small lemma to say that this is a sort of the result is sort of a hypergeometric integral. So I will define this part u in minutes. So this hypergeometric feature resides in the following. So if we choose the following parameterization for the standard index, right? So and then then you can see these are the boundary equations. These are the boundary equations for the phases of delta n. So and then basically you basically labeling these boundary equations by the corresponding power. So I think so this related to hypergeometric, I think this is from in algebraic geometry. So they consider integration along a polygon, for example, is in this delta n, right? So now and then whatever they have some factors like this. So they consider the boundary equations, which are polynomials for the polygon, and match it with some power. That's why I call this a sort of the hypergeometric integral. It's from something from algebraic geometry. They can consider they can construct hypergeometric integrals out of this way. So another interesting feature is that so you have a summation in here. So you have a sort of a multiplication type in here. So and then then this omega, so it's somehow is the generating functions for the exponential. So that's another feature. So in this so that's another features in this integral in these two parts. So so I think I'm running out of time. So please give me just 1 minute. So so I will give you one more examples, like to see the probably like a simplest example to see what is this integral. So let's just look at one single term in the one of the terms in a full second coefficients of P. So yes, once you understand one term, then you can understand others, right? So it's some rearrangement operators acting on this sort of this derivatives of symbol of P. So let's consider this leading symbol. So with coefficient Kij, right? So it's so D is the derivative in psi, and nabla is the basic derivations on non-commutative tori. So and then this sort of this contraction between contravariant and the covariant tensors. So it's then you get a polynomial in psi of degree 2 with coefficients. Here you have the derivatives of K. So which does not commute with K. So you have a coefficient in here. So
we do not see the page where you are. I mean, we see a fixed page.
Oh yes.
Thanks a lot.
Let me try to do this.
It was becoming too abstract, you know. Yeah. Okay.
So in this case, right? So this to compute the integration in psi, we only need the very first term in this exponential. So right, which means that we only need the exponential is 1 plus of this, right? So we only need the first term of this exponential. So and then this partial derivatives kills this psi. So then you see this coefficient in here. So and then this integration becomes looks like this. So because I assume this complexity about this matrix, so therefore there are not much more simplification about this part. So let's for example, let's look at the diagonal case, right? So for example, if the leading symbol is diagonal, it's like you have these different vowel factors. So K1, K2 along the diagonal. So this so then I can easily compute the inverse and the determinants. The determinant is the multiplication on the diagonal, and this is a single element on the diagonal. So now you have from the conformal case, you have 1K. Now you have this K1 until, for example, K1, K2, for example. So now if we are in a conformal case, like even K1 is equal to K2, then we can get a further simplification, right? So this then all these terms that are the same. So then we can combine the power. You have a 1 and an m over 2 because of this determinant. So and then if you do a simple change of variable, so if you look at what's inside and factor out this K0 and call this part a formal variable Z, so then this integral in a rearrangement operator is sort of of this type. it's a sort of an Euler type of integral of this Gauss hypergeometric function f12. So that's a because so I will stop here. So thanks so much. Sorry about running over time.
Thank you, Yang, for a nice talk. Let's thank Yang. Okay, are there any questions or comments?
Well, you know, I couldn't help to be reminded of quantum field theory computations when you were doing these integrals with Gaussians and so on.
Yes.
And also the link with hypergeometric functions. So, I mean, you know, there have been a lot of works on computing Feynman graphs from algebraic geometry and so on. So, I mean, it might be quite interesting to do a close link with these things. I mean, it's clear that it's related in the way you formulate things. I mean, the relation seems to be very clear, very strong.
Yes. I think yes, Masu and I and Askar. So we are looking at a potential way. I mean, yes, indeed, to find, for example, some graphic interpretation for this complicated
Exactly. You see, I mean, exactly, because I mean, the point is that when people do computations in quantum field theory, okay, they get incredibly complicated, as you know very well. So, I mean, here we are in a similar situation, and what is needed is an organizing principle like Feynman graphs that allows to really, you know, combine things in the right way and so on. Because, I mean, what happened in quantum field theory was quite interesting. You know, it was really done by Schwinger. And then it's only when Feynman entered the scene that things became, you know, sort of easy to grasp and to compute. So in fact, there was a saying at the time, which was that Schwinger had brought quantum field theory to an art, and Feynman brought it to the masses.
Yes.
So,
yes.
So I mean, here it is, I think, quite important to somehow, you know, make it more and more, I mean, to index the terms, to understand what they mean, to have some graphical representation and so on and so forth. I mean, but the content is there. So for instance, can you obtain the effort term by like we obtained with Farzad by looking at this example, which is not conformal, as you know, which is a product of two tori with different Weil factors.
I mean, for that, maybe, Young. Yeah.
I think it's yes. So this is sort of in the middle of a process to find the, you know, to sharpen the tools to reach A4 term. So
to reach the A4, yes. Okay, you mean at the moment we were with A2 and with Ricci curvature. Yes. I see.
Yeah. So yes. So on the other hand, so I think the main application, so to introduce this hypergeometric functions, for example, so if we want to verify the functional relations like that, right? So
this is very
using these building blocks, this f of alpha, I can do this without, you know, computing this f of alpha, and I can do this using the functional relations among this f of alpha. So that's
no, that's very convincing. Yes, certainly. I mean,
yes, that's a main advantage of it. So I think a more beautiful way, like linked to this, is like if we so in this during this verification, it's like it's really artificial because I know it is true.
Yeah,
right? So, and then try to match. But if we can find more sort of these graphic interpretations among these building blocks, probably these functional relations will have some more algebraic meaning. So that will be
also, you know, what is clear is that the type of functions that one obtains, for instance, as displayed in this formula with the, I mean, they have certain properties which makes them very close to algebraic geometry. And so, I mean, so what one needs to have is a good way to encode them. For instance, you know, in the paper with Farzad, okay, we have the results, but we don't have yet the way to encode the functions, which would be conceptual somehow. So, I mean, this is what is missing. And what we noticed with Farzad was that the same functions were occurring in transcendence theory. So in other words, I mean, it's functions which are generated by polynomials, rational fractions, and also exponentials. And I mean, in transcendence theory, for instance, there is this book by Waldschmidt on transcendental numbers. And I mean, these functions play a central role there. So somehow, you know, it would be nice to understand how they, of course, they are connected to hypergeometric functions, to see if, you know, the monodromy and so on can be interpreted. I mean, so there is a lot of work to be done, I mean, to understand things for the effort term I'm talking now, yes.
Yeah, I mean, for A2, it's quite possible that these calculations will be like computing one loop expansions in QFT.
Yeah, exactly.
Quite
I mean,
possible that it will come out like that. So, we are looking at that now.
Yeah, sure. I mean, you see, there has been a tremendous efforts which have been done in recent years. I mean, motivated by Dirk Kreimer. I mean, of understanding the link between finite graphs, motifs, algebraic geometry. Also, you know, this paper of Donzaghi and Kontsevich.
Yes,
which
periods, on periods.
Yeah.
Not periods. This is also something to look at because I mean, they define periods in general, and you know, then you get these very typical expressions. But one thing which at least, you know, I remember very well from what we found with Henri, I mean, in our paper, I mean, what was really important was that normally when you do ordinary differential geometry, you are working with the nilpotent formulas because you work with the exterior algebra. Whereas here, and typically in the formulas you were showing, one has formulas which involve when the scalar curvature, but they are no longer nilpotent. They involve the full formula with hyperbolic sign and so on, not just the expansion. They involve the full function, which is really quite different from classical differential geometry.
Yeah, I think another difference is that classically you have a square root of that sinh function divided by x for a hat genus, but here there is no square root. It's just the function itself. So it's a bit different.
But I mean, they are applied to different things. I mean, you know, this function is applied to something which is purely non-commutative.
Yes.
So I mean, it's like, you know, the non-commutative dimension, which is bringing in some formulas which are no longer nilpotent, and which look perhaps the same, but they are not quite the same. You know, they have their own life of their own. In particular, because they are full functions. They are not just expansions up to the dimension of the manifold.
No, that's right.
Yes, I think another link to this graphic stuff is that because here, for example, I consider this heat operator, right? So there is an exponential function behind. If I replace this heat operator by the power function, right, the zeta function, so probably we will see because I have this integration over the n simplex. Probably I think I might get this multi-zeta value functions.
Sure. Exactly. No, but that's why, you know, there is this literature which is a little bit difficult to penetrate, but with a lot of work which has been done, motivated by finite graphs. But okay, I mean, you know, it's there is obviously an analogy, really, and something very strong. I mean, the way you presented it, it's very strong. Yes.
Okay. Any other comments or questions for Yang? Okay, it looks like there are none. So let's thank Yang again.
Thank you.
Thanks.